Uh, Thank you, Evgeny. Yes. Let me just. Okay. Today, I want to talk with you about self-organizing maps. Maybe you have heard about them. Okay. Sorry for my poor handwriting. Why it's so slow? Okay. Self-organizing maps, or you can call them SOM, or you can call them Let me check that I will write it properly. Cohonen networks. Have you heard about them? Good. For some of you, so it will be repetition. Yes, it's kind of interesting type of neural network that it's an important feature that it organizes information by its own. So we don't tell, for some, we don't tell which the right answer is. The task of SOM is to learn. SOM looks on data. SOM learns data. It learns patterns. It looks on data and learn patterns. Important point of SOM. SOM is kind of inspired by biological brain, and in our brains, information is quite often organized in topographic way. What it means? Let me just add this note. So biological inspiration means it's like topographic way. What it means? It means that similar kinds of information are located close to each other. Like, for example, for how it's called, auditory systems and nearby neurons respond to similar sounds. Yes, and our brain builds its kind of a map. Topographic. Mapping. Yeah, so like, for example, this is our brain. And we have here area which responds on sounds. Oh, no, sorry. And for example, this area of our brain map responds on, I don't know, maybe some pictures or something like this one. Yeah. So, and SOM does something similar. So what is doing? It takes like this our complex, very high dimensional, big vectors of data, and turns it into kind of simple map where similar things they located close together, like here. And it's also, by the way, it's a very useful way to organize, to understand and visualize our data easily. Yeah, this is the main idea. Like, we steal ideas from biology and create this kind of topographic mapping in our artificial intelligence. Right now, any questions? Great. I'm going to next slide. So, Oi, where is it? So now let's talk a little bit about principles of self-organizing maps in very, very, very simple word. Yeah, it's kind of a sensory system. Like we have this, somebody calls them nodes, somebody calls them neurons who don't like, yes, let me just make it maybe. Wait, no, move away from here. This one, blah, blah, blah. So, and we have this, this is, we have connections, blah, blah, blah. We have connections, for example, here. Yes, this is how we can really easily depict SOM. So we have this sensory system of neurons, which it's an input vector. I don't have place to paint input vector, but let me. So we have this input vector. Input vector, which has D elements, for example. And we send these inputs to neurons. So we have this input vector. We send it to inputs to the neurons in the SOM. Yes. So this is like, let me call them neurons. Yeah, maybe I have changed the color because it's not very beautiful now. Can I change the color? Yes. This one. Yeah. These are neurons. Yeah. And important point that each neuron has its weight. Weights. Where you go? Yeah, each neuron has a set of weights. It's important. You can think on how can you understand these weights? It's like something which neuron expects to see. So what's happening? We have this input, and we present this input to SOM, and we compare it with weights of every neuron. And what do we need to do? We need to pick. Sorry. We need to find like one neuron in this grid will be closer to this input. Like what it means? It means that its weights will be more similar to their input vector. And we find this winner, and we call it best matching unit. Best matching unit. Yeah. And so what's happening? So we found our winner. We found a neuron which and weights of this neuron are the closest to our desired vector. We will talk about all algorithms also today, but a little bit later. Now I am describing you just like the core idea. So we have our winner, and first we need to update. We update a little bit, or maybe not a little bit, the weights of the winner. And wait. Oh, sorry. I'm very sorry. Let me just. Oh no. Yeah, nice. Sorry, it has some delays. Yeah. So we updates after first we updates winner weights, and we also update weights of of neighboring neurons, but less strongly than winner. This is key idea. So any questions? You can think about this like we have a neuron network with like only one layer. But everything is packed into the grid. And if you will zoom into any, I need to change the color again. If you will zoom into any neuron, like you can see connections of this neuron with other neurons. And like kind of they have nearby neurons, they have like communication channels to nearby neurons. And through these channels, if we have this connection, the learning signal. So we found this learning signal, it spreads to the neighborhood or the winner. So what is the key idea? Like when we learn our map in this way, nearby neurons, because we adjust, like we change the weight of winner, and we also change less, but we still change, we adjust weights on neighboring winners and nearby neurons and closer winners, neurons are weights are updated more. So what's happening here? The key idea is that nearby neurons, nearby nodes here, they learn to respond to similar inputs. Okay, so we change the winner and we change some region around it. Questions? And this is a basic principle of SOM. Okay. If clear, we can continue. Let me just add a note about this is communication channels. Communication. What I wanted to write. Oh, sorry. Let me just. So, sorry, dear colleagues. Can you see my screen again? Guys? Okay, I think it's working. Okay. Let's continue. Okay, please. Nice. Yeah, so we need to repeat this process when we learn. When we process learning, we need to this process to many inputs. And like in this case, map organizes itself. So like nearby neurons, they learn how to respond to similar inputs. Okay. If you have any questions, please feel free to stop me and ask them anytime. Okay. What I wanted to say next. I hope you mentioned that SOM is it supervised or maybe you noticed it? Is it supervised or unsupervised learning algorithm? Yes, unsupervised, because like you have this vector, you have your data, you upload them to SOM, and SOM somehow with some mathematical magic I will show you this magic a little bit later, but it adjusts somehow its weights. So yes, it's an important point if you've been asked. SOM is unsupervised verbal learning. Here. I'm sorry, guys, my handwriting is something. You are good. Algorithm. Yes. Yeah, as I said, that means that during training, we don't give any labels or correct answers to the network. It also belongs to the class of, how it's called, competitive. Yes, competitive learning. Oh, yeah. How to write it? Competitive. Why is competitive? Because neurons, they compete with each other. Who will be the winner? Yes. And it's a little bit different. Like for example, like error correcting learning, when we compete the output. Oh, sorry, when we compare the output with the target label and correct errors. Yes. Learning. Okay, but we still can use labels in a SOM. And now let's imagine, again, let's think about a SOM as a map. Again, the same picture. A map with neurons, somehow connected neurons. So we have this kind of grid, and I will not paint everything, but in interconnections of this grid, we have neurons. Yes. So, as I said, each vector has its weight vector. Oh, sorry, each neuron has its weight vector, and sometimes this weight vector is called like prototype pattern. And for every input vector, by the way, it's important when you upload data, you upload input vector to here, and let me just change the color, and I can paint for you more colorful. Yes. So we have like one pattern here, for example, we have one pattern here, different patterns. So like, do you remember that vectors which correspond to several, to same like thing, they are used to be located together. And yeah. So each neuron has its weight vector, and every input vector, when you upload vector to compute to SOM map, for each neuron, you compute some discriminative function. It's called discriminative. Function. In practice, it's usually just distance between like input and each of neurons' weight. Yeah, so like distance between two vectors. You have learned it already. And as I said, the closest neuron is winner. And sometimes it's mentioned like neuron like attracts that pattern, because like we have one pattern here, one pattern here. Let me just P1, pattern 1, pattern 2. So like one neuron wins, so it like attracts one pattern, and another input may be attracted to another neuron. So like we find the closest neuron, so like our input is attracted to winning neuron. And so we get pattern, like for example, here we have pattern E, here we have, okay, pattern 2, pattern G, for example. Let me just remove it and just pattern G. Yes, but do you see any problems here, colleagues? We have trained our like unsupervised learning SOM metric, SOM grid. And what shall we do now? Like in the end, like we uploaded a lot of data. I'm sorry, we have a question to you. Okay, everybody can hear. Nice. What shall we do? And now we basically have a huge matrix with vectors in this, like maybe not matrix, maybe it, but like we have this grid structure with neurons, weights in these neurons. We trained it on a lot of data. What shall we do next? How we can use it? Because like the problem, what I see now, like our learning is unsupervised. Like we only have like this huge data structure with neurons, somehow organized maps with just like neurons which attract some data. But our neurons are still unlabeled. Like we have this huge data structure. What shall we do now? Like we cannot say, I mean, our map, it doesn't say like, for example, this is a cat, or like this is digit 8 or something. So like in this condition, it's useless. What can we do now? We can also add labels to our samples. Yes? Oh, do it, please. Thank you. Yeah, we can add labels to our samples, and this is how we can turn our unsupervised learning to supervised. So we can add supervision under training. Like how it's happening? We take again our untrained SOM. We take again our trained, it's important, trained SOM. We feed labeled samples to our SOM, and look which samples hits, like which labels hits neurons on each region. What does it mean? Like for example, let's look again on this neuron, and this is our trained SOM. We took it and we uploaded more samples to this SOM, and now we start to gain statistics. Like for example, for this neuron, after our training, we see that it attracts like label 1, label 1, label 8, label 7, like, and for example, like again label 1. Yes, so we uploaded again vectors and same vectors, and these vectors with these labeled vectors, they hit our specific neuron. Yes. And in this case, so we collected these statistics. And what can we do? We can like again on this list of labels, and we can say, okay, we can find like the majority neuron, the majority label, and assign it to our label. And we can find this and assign it to our neuron. So for this neuron, we collected that these labels hit these neurons. So for these statistics, we see that the most common one is which label? It's not this question has no hidden thread, so L1. Yes, L1. So we just take like the most majority label, and we derive that, okay, this neuron will be marked with L1. Yeah. So again, so what's happening here? We upload vector. This vector attracts some neuron attracts this vector, and we can and we have to remember the label from this vector. And after that, after all this training, in best case, all our neurons will be labeled. And now we can use, when all our neurons will have these labels, we can use SOM for classification. Is it clear? Any questions in this moment? It's important thing. So yes. It's also, by the way, after this labeling, it gives us very nice visualization. So you can color when you have this all this labeled map with like this is L1, this is like L3, this is like L4, blah blah blah. You can color your map with labels, and it gives a very nice visualization. Like for example, when different colors represents different labels. Okay, nice. What I wanted to add here. So, and by the way, important point is that this approach, you may notice it performs like kind of dimensional reduction. So you have data with n features. You take this huge vector with n features and maps down just in 2 dimensions. Perfect. Like to the 2D grid. Yes. And usually for the visualization, we usually use 2D grid, but sometimes each neuron may have like 4 neighbors, sometimes it may have 6 neighbors, like, so it can be rectangular or how it's called, okay, 6 neighbors, you understood me. Hexagonal, yes. Yeah, but algorithm itself is kind of generic. So like, you may use even like kind of, you may turn your grid to a cloud. For example, it can be 3D and can be 4D. But of course, you need to adapt like this distance function for dimensionality of your SOM grid, SOM matrix. Questions, dear colleagues? So, okay, we trained our matrix first. After that, we uploaded like labeled vectors, and this is how we colored our map with labels, and we are happy. Okay. Okay. Do we need to? No, I think we have more time. So yeah. Like this is our ideal design. We want to have this labeled map with adjusted weights and with proper function. Now let's talk a little bit, let's look at each step of SOM algorithm, step by step. Okay. First is SOM. Yes. And it has 3 phases. First is initialization. Let's talk about first. Initialization. Then this I think you can guess what's happening, because it's kind of standard for many neural networks. So we initialize, we have this our map, and we initialize all weight vectors of each neuron with what? With small random numbers, as usual. So all Small. Mhm. Yes. So like we randomize it a little bit. So now our neuron, like each neuron starts in slightly like different, how to say it, like place in a feature space. So yes, we randomized our neurons, now our neuron weights. Very nice. Next is competition, competitive learning. Competition. As I said, each neuron is equipped with discriminant function. You remember it. Vector plus. Yeah. And usually,
Yes. So this one, I asked him for an update on this one. There has been no update from Steve for a long time now.
I'm sorry, you don't see the screen?
I see the screen, so I don't know.
So you see updates.
Yeah, I see what you're writing.
Okay. Sorry to hear that you have problems, but maybe you can check with recording later. And with, I will also pause this, my disgusting handwriting. Okay. So like when competition starts, what's happening? Like for each input, for every input pattern, like you, or for each feature vector, you feed each input, like each vector is fed to all neurons. Each neuron processes this, and each neuron uses this, our blessed function, our discriminant function, to like computes its score using this function. And like, as I said, it's in practice, it's usually distance between two vectors, and like between this input vector and between neuron weights vector. Yeah. So each neuron computes value of this function. And after that, we take a centralized view. We choose, we look like we'll look on all these scores, and we choose like the neuron with smallest value. Who is the closest is the winner. And the winner is called, as I said, just like I want to again mention it, it's best matching unit. Matching unit, or let's you BMU. Short, simple, elegant. So if so again, neuron with smallest, neuron with smallest FD function, like this discriminant function, is the winner. Yeah. So like if neuron matches the vector perfectly, the distance will be 0. And the neuron is clearly the best for this pattern. Yeah. So like over time, each neuron will try like to collect patterns with like lower distances. Okay. For now, questions do we have? Okay, 10 more minutes and we can go on break. Okay. And third step of the algorithm, a third phrase is cooperation. Let me just cooperation. So again, we have this grid, blah, blah, blah. So how to formulate it? So on competition phase, we picked a winner. Yes. So like for this particular vector, we picked for this particular step, we picked a winner. And we know also now that the neural node of weight vector is closest to our input pattern. And in cooperation phase, we like ask what we do with this information now. And we can do a lot of exciting things. And cooperation is about like exciting a neighborhood. So like, again, we have this lattice. Let me just add that it's like, this is our neuron winner. And it matches to pattern, to some pattern. For example, pattern E. We chose winning neuron. And we now need to change not only adjust not only weights of single neuron, we want to spread this information to all neighbors of this winner. So a group of, so we have partners, let me just, we want to spread this information, information to neighborhood. Wait. Around the winner. Yes. So like and group of neurons, let me just mark them somehow. Yes. Wait, no, not this color. This one. So yes, and the group of neurons, nodes around the winner, becomes excited and will update their weights. Let me just neurons becomes so-called excited. So in this phase, what do? We determine neighborhood, like who is around, because it's also kind of a trivial question, like how many neurons, like how large should be our neighborhood? Like how many neurons will we change? Or maybe sometimes we will cover the whole grid. Who knows? And all neurons in this neighborhood, they will be marked as excited and will be affected by learning step. It's like a same idea you see in biological system. This is like the updates are spreading in a neural system. Yes. What else I wanted to add? Yes, and in simple case, this discriminant function fd is usually usually Euclidean distance between vectors. Nothing strange between input and vector. Okay. What else I wanted to add here? So yes, so this winner, it creates so-called like attraction field. And all winner and their neighbors, they slightly move their weights towards the input vector. Okay. Okay, so it's called, I forgot, attraction field. Attraction field. Okay. Let's have break now. So because now I will write some formulas. So we can. So let's have 5 minutes break. And we can go jump into formulas and enjoy them.
I have a
Yes.
question.
Sure.
I didn't really understand what each neuron contains or what it gets. I understood that the closely related parameter gets grouped together in the 2D map, but I didn't really understand what each neuron gets.
Each neuron gets, so each neuron itself has like, it has set of neighbors around it. And it has, each neuron has weight vector with the same dimension. Like the same dimension. And when we train our map, we just take weight vector from each neuron. Sorry. And we take weight vector from from data. So these two vectors, they have same dimension. So we just calculate the distance between them.
Okay.
And that's all.
Okay.
Did I answer your question?
Yeah. Thank you.
Great. Okay, colleagues, 5 minutes break, just like stretch a little bit and I can jump in some technical details. Come on. Oi. wrong? Sorry. Okay. Now we can continue. Now let's dive into the most interesting parts, technical details, formulas, all these delicious things. So just a reminder if you forgot, we have a discriminant function. Yeah, and classical SOM, it uses, it just, in these functions, is simply like just L2 distance, the Euclidean distance between two vectors. So we calculate the distance between input vector x and weight vector of a node, of each particular node. So we can write formally, let me just send this one. So we can formally write this one, it's just like L2 distance, where x1 here is coordinate of input feature vector, one coordinate, and number I, and W is coordinate, the same coordinate of the weight vector of this particular node. So we need to calculate it for each node. Okay. And by the way, for many implementations, you may even like remove this square root and use only square distance because the result will be the same. Like if you want to reduce calculations, don't hesitate to remove it. Because like square root doesn't change which node has the smallest value in this case. but it makes our computations cheaper. Yes. So we calculate all these distances. And after calculations of these distances, we are finding a winner node. We found it. We called it BMU best matching unit. We found this winning node, and we found also index. So we found this node, and we found index. Let me just index of BMU. Yes. So it has we found our BMU, and we also know coordinates of this unit, like I mean on a grid, where it is located on the grid. And for next step of algorithm, we need a notion of topological proximity. Let me write it. Do it, please. Please change the color. Thank you. And we need this notation between nodes on the grid. Who is located where? Proximity. Topological proximity between nodes on the grid. Yes. And now we can also introduce distance on our lattice, on our grid. And we can write it as CEJ. It's like simply a distance between, for example, node E and node G on the map. Okay? And it's important, like, not in feature, it's not in feature space. Yes, so we will use this lattice distance, and we will use this distance. Oh, let me just call it distance. Distance between E and between E and G, between these two nodes. And now if we will use this distance, it will help us to tell how strongly like each neighbor of BMU of our winner of our best matching unit should be affected during learning when we spread influence from this BMU to other neurons. Okay? Nice. Let's go next. Questions? We slowly approaching to the more bigger formulas. No, number 7. Yes, now we want to explain how we let's explain how we control like neighborhood around winning node. And we do it using hyperparameters. Controlling. Wait. Yes. Why it's important? It's very important state because yes, we use it using hyperparameters, which are similar for all map. and prevent our pattern, like one pattern. What we want to avoid? We want to avoid one single pattern for taking over the whole map. We don't want one pattern, we don't want one vector to spread influence across all over map, because otherwise we cannot use it after it. I mean, like, we cannot classify it if if one pattern hits whole map. And to prevent this, we define a neighborhood coefficient G. And for what are we calculating? For every node in a grid, for every node in a map, and for our BMU, for our winner, we compute exponential I think I like this way more. Yeah. In minus S E G square to sigma. Square as well. As I said, SIG is a distance between on the lattice between I and BMU. So, like, first of all, we calculate this distance, and sigma, it's like kind of parameter which adjusts like the size of our neighborhood. So like our neighborhood is decaying, and now if we use this coefficient, is our neighborhood is decaying function of distance. Like it means like the larger distance between winner and any random neuron in our map. What? Sorry, I just noticed some garbage in my notes. Don't worry. So like so CJ is our distance, sigma is our parameter which controls the size of our neighborhood. And like the larger distance is like when distance is larger, the smaller G becomes. You see in these formulas, in this formula. When distance is large, the G becomes smaller. And on 2D grid, this lattice distance, let me just, yes. Yes, it's like, again, it's just a Euclidean distance on 2D grid. And between node with coordinates, with coordinate I and BMU. Okay, let me just add this. What's happening? Yes, and we can write it like this one. S between I and our best matching unit. Don't forget it, please. How you can calculate this distance? Again, Euclidean guide. Xi minus X BMU square plus and X and Y, they are just coordinates here. They're just coordinates of the nodes. So it's like you have X, you have Y, you have our beloved best matching unit, and we have our node number E. So let me just add the node X, Y, they are just coordinates. of the nodes, yes. And important point here, let me just maybe, yes. An important point here that sigma itself, it also changes over time. But again, the same exponential decay rule. Like, and t here, I mean time, and I mean time, and I mean just like iteration, like iteration step. So like we have, let me just add some notes. I want to highlight this one, and I want to highlight this one as well. Yes, again, it's standard exponential decay used here. You can write it like again, exponential t multiply tau 0. Oh, divide, sorry. T divide tau 0. Yes. And it's like, it's not a rocket science. It just says that, it's just, how can you read it? It's like the parameter which controls like how weight is neighborhood in, how weight is neighborhood is a function of iteration number. T is iteration number, just number of data, number of vector. Okay, like you have 10 vectors and you have 10 iterations. Good. T is just like iteration.
So the more we go on with the iterations, the less neighborhood we consider.
Yes. And it's like interesting points that like first vector affects more.
Why would we?
Because like first in first iteration, we just slightly shift the weights, and other iterations, they adjust it. But like, I will return to this. It's a very important point. It's a very important note.
So the iteration is like setting the direction.
Kind of. It has stronger influence, but you have other iterations after this, so you need like enough amount of data to adjust it to make it more smooth. But yes, but like this initial shift will be set by first. And that's why, by the way, you need to shuffle your vectors very carefully. Like, for example, if all first vectors, like, for example, if you, in your data set, all vectors, like first 10 vectors, very roughly speaking, first 10 vectors will be labeled as L1. Your whole map will be shifted to L1. Great. What I wanted to say, I wanted to touch on this iteration number. So yes, and it's important that it's the beginning of training, our neighborhood like is wide. So this region is wide, and we are aggressive and move, and we like adjust, we change many nodes. Later on, future iterations, this sigma becomes smaller. So like t is growing, sigma becomes smaller, and our neighborhood like shrinks. And we are just more careful with our weight updates, so we make more like careful adjustments of their weights. Yes, so first of all, sigma is yes, sigma 0 is initial value of radius, like you can play with it a little bit. Tau is hyperparameter. Let me just write it. Yes, it's not t, it's tau. Tau is our hyperparameter, which tells us how fast the radio decays. Again, you can adjust this parameter. Yes. What else? So yeah, to summarize, like as we said, winner takes it all. BMU will be a center of gravity with stronger effect, and all other nodes will be affected less in these formulas. Yes. And by the way, you can play with choosing sigma and tau, sigma 0 and tau 0. Sorry, this and this. Oh. Yeah, you can play with choosing these guys. Why do we need it? Why do we need to adjust them? We want to, like in extreme cases, in trivial cases, like we don't want the pattern to also call this spawn on the whole. We want, as I said, we don't want one label to cover the whole map. Yes. We want like that our each pattern will occupy different region. We don't want one pattern cover all our map. Okay. Questions, dear colleagues? Yes. And what else do I want to? And now we have only one part left. So like we recalculated, our one part left is adaptation phase. Of the SOM. So we decided like which neurons will we touch with our changes. Like we found our winner, we found the region, we found all neighbors, and now we want to affect these neighbors. Adaptation phase. Yes, it's our last part of algorithm. And this is where we usually update the weights. Now finally it's time to learn. Update the weights. Okay. Let me just first, yeah, we want to compute, we want to compute these weights, compute, tech. Okay. Yeah, compute new weights. So, and for each node, we compute so-called weight change. Obvious. And let's delta omega new t multiply g x minus omega. And let me make this here. Okay, this is formula. Now let's read it step by step. So what's happening here? We have this our pattern vector, we have our feature vector, and subtract the current weight vector of this one. And it gives us kind of direction, like where do we want, in what direction do we want to move our weights? And then, oh, sorry, I think I need to write a little more careful. And then we multiplied by G. G is so-called, let me just go write it. It's a neighborhood reduction coefficient. Mm. Reduction coefficient. Reduction. Hope you will understand my handwriting. Sorry, guys. Coefficient. I'm doing my best. Oh, yeah. Yeah. Well, what's important point about this neighborhood reduction coefficient? For the BMU, do you still remember what BMU means? Best matching Q unit, yes, our winner. I just checked that you are not sleeping. Yes, it goes close to 1. For neighborhood, it smaller, like in comparison with best matching unit. For like far nodes, it should be very, very small. And G tells us how much the node belongs to the neighborhood. Like, is it belongs or not? And yes. And finally, what do I want to add in the end? We multiplied by the learning rate. As the learning rate, this is learning rate. This function is. And this is formula of our learning rate. And again, iteration. And this is extra reduction factor. It again controls how aggressively do we change. How aggressively do we change even BMU? Because like we also want to adjust this reduction factor will also affect. Maybe I can close. Yes. And formula of learning rate, I think you can guess how it looks again. It's again is exponential. We have this hyperparameter and multiply exponential of minus t again tau. Yes, and so this is initial learning rate. Let me just again. Again, t is the same as iteration index. Tau n is how fast the learning rate decays again. How fast learning rate decays. Decays. And this is initial learning rate. And T is again the same iteration in the index, and it was then it was like yes. So we use this learning rate to adjust. We calculate this and put it here, and we use it to adjust our weight changes. Yes, so we updating our new weights. Okay. And so like in this, when you train your SOM models, you need to play with hyperparameters. So like let's just like list all hyperparameters which you have of SOM. Hyper parameters of SOM. So yes, what do you have? You have sigma 0. It's like initial like radius of neighborhood. You have tau 0. It's like decay rate of the neighborhood in the previous formulas. You have nu 0. It's initial learning rate. Like, so we change learning, and like distance affects learning, distance affect like radius. And tau nu is like our rate of decay rate of learning rate. So what I wanted to say here, to add here. What I wanted to add. Yeah. Important point. Like, by the way, questions. I feel that you're cooked, but like we're almost over. Like you can also play, like you can choose like this initial neighborhood big enough. So even like if like for example, even if some pattern hits the corner of a map, like its neighborhood still covers the lattice. Like what do we want to do? Why do we want it to be big enough? Because we want to avoid isolated locations. Okay, we need to cover the whole map. We don't want to have like isolated islands in our map which will never get updated. And it's also important in training to shuffle data before you before you feed it to the algorithm. Why? As we said, like if in the beginning we will have the same patterns, like a lot of same patterns in the row with same labels, your map will become dominated by this pattern. Yes, because like they have more influence. And like if you randomize them, if you feed your grid in random order, it leads like more scholastic, it leads like more balanced learning, and it's basically much closer to biological systems. Like these are biological systems to learn. Yes. And I think it's all what I wanted to say. Or I wanted to tell you today. Yes, any questions? Or maybe your questions will appear tomorrow. Like tomorrow we also have, unfortunately, we have an early lecture, but we need to be strong. Okay, if no questions, I will stop sharing, stop recording. I think we have 10 more minutes. Okay, maybe I will just try to be faster tomorrow because tomorrow lecture is a little bit bigger. Okay? Good luck, dear colleagues. I will upload this precious file for you.